All right, so I think this is recording. Let's take a look here at number 2. We're given a polynomial function, and we're asked to find the zeros of this function. So we set this equal to 0. We start out by looking to see if there's any greatest common factor among the terms. It doesn't look like there is. And also to make sure that this is in standard form with no missing powers, 4, 3, 2, 1, and the constant term. So it's not. So we can look at the factors of the constant term as our possible numerator. So the factors of 12 are the integer values that divide 12. And we look at the factors of the leading coefficient. Factors of 4. So the factors of the constant term are the possible numerators, and the factors of the leading coefficient is the possible denominators. So my list of possible, no guarantee that any of these will be 0, but the list of possible rational zeros. All right, so we take each of these numbers and divide it by 1. So that just gives us this list back again. Now we take each number and divide it by 2. Now if there's any of them that's already in the list, we don't have to repeat it twice. So we've got 1/2. 2 divided by 2 is 1, and we've already got that. 3/2. 4 divided by 2 is 2, and we've already got that. 6 divided by 2 is 3. 12 divided by 2 is 6. So we've got all that we need here. All right, so let's begin looking through this list to see if we can't find a 0. So I'm just going to try one. I'm just going to go through the list. Some of you might be gifted enough to look at it and kind of see which numbers are smarter to check first. But just make sure that you keep an organized track of the ones that you've already checked so you don't waste time checking them more than once. So you can see this is not going to give us a 0. I doubt if -1 will either, but let's try it and look and see. And we can see that it doesn't. This does not add up to 0. So we've tried +1 and -1. Let's try 2 and -2. Doesn't look like this one's going to work out either. Yeah, because look how big this is going to be. This is not going to add up to 0. I don't even need to keep going any further. And this one's not either. So 2 and -2 didn't work. Let's try 3 and -3. Well, 3's not going to work. Let's try -3. Now this one has a chance. There we go. All right, so we found one. But this gives us a third degree, so we still have to keep looking. We're not ready to try to do the X method on it yet. But we don't have to go back and try any of the ones that we've already ruled out. It could be that this has multiplicity 2, so let's try it real quick. Doesn't look like. Yeah, that's not going to give us 0. So we're done with 3 and -3. We did find out that -3 did work. So let's try 4. And if that doesn't work, we'll try -4 and we'll just keep going through the list. I generally hold off, probably just like you do, to try the fractions last, but eventually we might have to. And this one definitely gives us a 0. All right, so and with 4x squared minus 1, we'll be able to factor this as a difference of perfect squares. So let's return up here to f, write it as 0 equals. We found that -3 was a 0, so in factored form, that's x plus 3. We found that 4 is a 0. In factored form, that's x minus 4. And now we have 4x squared minus 1. That's a difference of perfect squares. So that factors to a plus b times a minus b. So now we have this completely factored, and we can list our zeros. We've got the -3, a positive 4, a -1/2, and a positive 1/2. The original polynomial function was of degree 4, and we have 4 different zeros, so we found all of them. We don't have to come in and list the multiplicities, but they are all 1, they're all odd, so at each 0 the graph is going to cross over the x-axis. All right, well, I hope that helps, and I'll talk to you later. Bye.